Hello, and this is an introduction to the key concepts underlying electricity and the creation of electric circuits. In part 1, we take a look at charge. You might remember that atoms consist of three types of particles. By far the smallest of these particles are the electrons, which move around the outermost part of the atom. The two other particles are the protons and the neutrons. These exist in the centre of the atom, which is called the nucleus. The nucleus is, in reality, mind-bogglingly small. Although so are the electrons, the atom, in fact, is mostly made up of nothing at all. Now, if we could put two protons next to one another, they would do something very strange indeed. They would experience a force that would cause them to move away from one another. We say that two protons will repel one another. If we were to perform the same experiment on electrons, we would find that electrons too repel one another. Putting a proton and an electron next to each other, we would find that the particles in fact experience a force towards one another and attract. And when we put two neutrons next to one another, they in fact do nothing at all. In fact, we could place a neutron close to a proton or an electron and we would not see this force of attraction or repulsion. Scientists needed an explanation for this observation and decided that objects can hold a property that we now call charge. Charge doesn't appear to have any other cause other than just being a fact of reality. Because of this, we say that charge is a fundamental property. Why are particles charged? They just are. Not only that, charge is a value that can be both positive and negative. Scientists have decided that protons' value for charge should use positive numbers, and that electrons for charge should use negative numbers. We therefore say that protons hold positive charge and electrons hold negative charge. The unit we have given for charge is the coulomb. In reality, it would take many electrons to create 1 coulomb of charge. How many, you might ask? 6. Million. So, with our new property charge, and the positive and negative values it can hold, we can now easily create a rule of thumb for whether objects should attract or repel one another when charged. If the charge of two objects is the same, for example, when two protons that are both positively charged, or for two electrons that are both negatively charged, then those objects will experience a force away from one another and repel. If the charge is opposite, for example, when we have a negative electron and a positive proton, then the objects will attract. And what about neutrons, you might ask? Well, they hold 0 charge. When we want to use charge in mathematical equations, we use the symbol Q. When we give a value for charge, we use the unit coulomb or the letter C. For example, we might say that Q equals 3C, meaning a charge is equal to 3 coulombs. But what does all this have to do with electricity? Well, for that, we need to learn about electric current. First, let's take a look at a wire. A little closer than that. Closer still. No, much closer. Let's really get inside the wire. Because a wire is made of metal, we notice something odd about some of the electrons. They do not have to move around the nucleus and are free to move to different parts of the wire. We call these free electrons. When free electrons are given energy from, for example, a battery, they can then move through the wire to form an electric current. In an electric current, these electrons will flow around the entire circuit until they reach the battery again. We measure electric current in amperes or amps, and 1 amp is equal to 1 coulomb of charge moving past a point in our circuit in 1 second. So just imagine our bucket of 6 million electrons passing by in 1 second. That would be 1 amp. When we want to use current in mathematical equations, we use the symbol I. When we give a value for current, we use the unit ampere or the letter A. For example, we might say that I equals 3A, meaning that the current is equal to 3 amps. Now, you might be wondering, what are those electrons useful for now that they're travelling around a circuit? To answer that, we need to explore our third concept, voltage. To understand voltage, we must stop thinking of electrons as simply charged particles. In fact, they are charged particles that can hold different amounts of energy. I like to imagine electrons as carrying small suitcases of energy as they travel. An electron will be given this energy at the battery, which it will then carry around the entire circuit until it reaches a component that requires energy, for example, a light bulb. The electron will then give the light bulb its electrical energy, which the light bulb will transform into light and heat energy. The electron will then travel back to the battery where it will be re-energized, ready for a new lap of the circuit. When we use the word voltage, we are referring to the amount of energy that is transferred per coulomb of charge. So, for our analogy, it's the amount of energy that our bucket of energy-carrying electrons are giving to components like light bulbs or receiving by components like batteries. When we want to use voltage in mathematical equations, we often use the symbol V. When we give a value for voltage, we use the unit volts or the letter V. For example, we might say that V equals 3V, or that the voltage is 3 volts. Finally, you might wonder how energy is taken from the electrons. To understand that, we must explore our final concept for this video, resistance. Wires have a relatively low resistance, meaning that electrons do not have to spend much energy travelling through them. However, some components are much more difficult for electrons to travel through, and so they lose some energy travelling through them. This acts to slow down the electric current and causes the electrons to lose energy to that component. In this regard, it might be useful to think of an electric circuit like a pumped water system. As the water pump gives the water energy to flow, an attached water wheel might slow this current down by taking energy from the system. In this example, our battery is the pump giving energy to our electrons that flow around the circuit until they are met by some resistance that takes the energy from the current. In this example, a light bulb. When we want to use resistance in mathematical equations, we use the symbol R. When we give a value for resistance, we use the unit ohms, or the Greek letter omega. For example, we might say that R equals 3 ohms, which means the resistance has a value of 3 ohms. With these new concepts, we can begin to understand a very important relationship in electric circuits that is called Ohm's law. The core understanding of Ohm's law is that if the resistance of a circuit is increased, then the flow of charge will slow down and the current will decrease. However, if more energy is provided to the electrons by supplying a higher voltage, then the current will increase. It is this constant battle between voltage and resistance to control electric current that is the key principle to Ohm's law.